Bismillahirrahmanirrahim. Assalamu alaikum. Hello and welcome to lecture number 20 of Algebraic Topology. In today's lecture, we will discuss dimension axiom for singular homology, and then we will discuss the functor Hn, okay, from in the case of singular homology, and then we will see the case path connectedness and homology, and what will be the effect of path connected components on the calculation of homology. Okay, so we have already discussed these two things for simplicial homology. So for example, we discussed the functor Hn for simplicial homology, and we have already seen the results that what will be the homology groups if we have path connected components, and in particular we discussed about H0. Okay, so let's start with today's lecture. So before going to dimension axiom for singular homology, let's have a look at the axiomatic definition of homology. So we reviewed these axioms in a lecture before. Then now what are the axioms for homology? So these are the Eilenberg-Steenreuter axioms, and in one of the axioms, so if you see them, we have dimension axiom. So axiom number 7 is dimension axiom. So it says that if we are calculating the homology group of a point, so this star represents a point, okay, so a point, then the homology group is Z if n is 0 and it is 0 for n not equal to 0. Okay, so we will see that this singular homology satisfy these axioms. Okay, so we may not be able to prove all of the axioms for singular homology, but whenever possible we will try to see that singular homology actually satisfy these axioms. Okay, let's start with dimension axiom for singular homology. So you can also take it as an example for the calculation of singular homology as well. Okay, so let's start with this calculation. What do we have so far? So we have these free abelian groups, and what is Sn plus 1x and Snx. So what are these free abelian groups? So these free abelian groups are generated by, okay, so are generated by singular n simplex. Okay, so what is a singular n simplex? So singular n simplex is basically a continuous function from standard n simplex to the topological space X. Okay, so this is generated by all singular n simplices inside this topological space X, and similarly we can define Sn plus 1x up to so on. And what are these maps? So these are the boundary maps which are calculating the boundary of the elements of Sn plus 1 inside this and up to so on. Okay, so it should be plus 1, and it should be n, it should be minus 1 up to so on. Okay. So if we want to calculate the homology of a point, then we should know all of these groups, and we should know the boundary maps as well. Okay, so let's try to see what kind of points are there in Snx and for any n. So Snx, so that's what we are trying to see, where x is a point. Okay, so Snx, as we have seen, that is generated by all singular n simplices. Okay, so basically I'm trying to see how many maps, continuous maps, are there from this standard n simplex to x, but in this case x is a point. Okay, so if we are trying to find a function, okay, so if we are trying to find a function from delta n to a space which has only one point, then of course you can see that there is only one possibility, and the possibility is that every point of this space, this standard n simplex, is going to the point. Okay, so we don't have any other possibility. Okay, so in other words, we can say that there is only one singular n simplex when x is a point. Okay, so we can say that Snx is generated by sigma n. So let's call it sigma n, where n denotes the dimension of this simplex. So it is generated by only one element, and of course we can see that up to so on, Sn, Sn minus 1, S0, S1, so all of them are generated by one element. Okay, so up to so on, so S0 of x is generated by sigma naught. Okay, so we know that what is a zero simplex, so it's a point. So basically this sigma naught is a function from one point to the point x. Okay, so now we know all of these free abelian groups. Now let's try to calculate the boundary of this sigma n. Okay, so how to calculate the boundary of sigma n? So we are just going to apply the definition. So this is equal to minus 1 raised to power I. This is sigma n restricted to v naught up to so on, and we delete this vertex vi up to so on vn. So that's how we calculate the boundary. And in the last lecture we also discussed that implicitly we are assuming some things about this thing, because when we delete this vi, then this is not really a standard n simplex, but in fact implicit in this definition is the fact that we are taking, and so when we are taking sigma n restricted to this, then in fact we are taking another map from a standard n minus 1 simplex to delta n, and then we are basically we are replacing this thing with the image of this standard n minus 1 simplex, which lives inside this standard n simplex. Okay, so that's something we discussed in last lecture. So that's the boundary of this thing. Okay, now what do we know about sigma n? So it's a constant map, and it maps each and every point of this standard n simplex to that one point. Okay, and when we restrict this sigma n to a subsimplex, okay, so in other words, as we have discussed this, that I am taking when deleting this vi, I am taking the rest of this as a standard n minus 1 simplex. Okay, so sigma n restricted to this standard n minus 1 simplex. So of course this should be equal to, so minus 1 raised to power I. So when we restrict this sigma n to standard n minus 1 simplex, then we have only one option. Okay, so how many continuous maps are there from standard n minus 1 simplex? Okay, so let's say I have a map from standard n minus 1 simplex to x. Okay, so once again x is a point, so how many maps are there from this standard n minus 1 simplex to x? Of course there is only one map. Okay, so in other words, whenever we will restrict this sigma n to a standard n minus 1 simplex, then we are going to get only one element, and that element is basically sigma n minus 1. Okay, so this n is independent, and this I varies from 0 to n. Okay, and this sigma n minus 1 is fixed, because in each and every, for each and every I am going to get exactly sigma n minus 1. Okay, so let's see what we have so far. So we have Sn of x, which is equal to generated by sigma n, and we also have the boundary. So the boundary of sigma n is equal to summation minus 1 raised to power I, where I varies from 0 to n, sigma n minus 1, and which is equal to, I can take sigma n minus 1 common because it is independent of the index, this indexing variable I. So this is equal to minus 1 raised to power I is equal to 0 to n. So if I'm adding these powers of -1, then what is the answer? Okay, so let's try to see. If I add one element, and -1 is to the power 0 is 1, so that's why I'm going to get 1. So for n0, okay, so for n0 I have 1. If I have n is equal to 1, then I am adding 1 minus 1, because -1 is to the power 1 is 1, and so I will get 1 minus 1. So this is the case when n is equal to 1. Okay, so let's see the case when n is equal to 2. So 1 minus 1 plus 1, so basically I'm going to get 1. Okay, so this is the case when n is equal to 2. So we can say that when n is even, of course we can generalize this thing, and we can say that this is equal to sigma n minus 1 when n is, okay, so this is 1 whenever n is even, so n is even, and this is equal to 0. Okay, so this is equal to 0 when n is odd. Okay, so these are the boundary maps, and these are the images of the boundary maps. Okay, now let's try to see the homologies, the singular homology in this case. So let's consider this Sn, and let's try to calculate Hn. Okay, so Hn of x is equal to Zn of x quotient with Bn of x. Okay, so we have two cases, of course, if n is even. So in the case when n is even, so we have already seen that this Snx is basically generated by one element, so it is isomorphic to one copy of Z. Okay, so it has rank 1. And what about the boundary map? Okay, so in this case we have taken n to be even, so when n is even, then the image of this is sigma n minus 1. So in other words, this thing when n is even, okay, so n is even, so when n is even, then this sigma n is basically isomorphism, because this Sn minus 1x is generated by this sigma n minus 1. Okay, and when n is even, then the image is sigma n minus 1. So that's why we can say that this partial nx is basically an isomorphism. Okay, if it is an isomorphism, then what about the cycles? So what about the elements which are going to 0? So the elements which are going to 0 will be just 0. So and this is equal to 0 if n is even. Okay, so let's see the case when n is odd. So when n is odd, okay, so n is odd. Okay, so now I want to calculate this Hn of x, which is equal to Zn of x quotient with the boundaries. Okay, so if n is odd, then of course this is of rank 1, this is a free abelian group of rank 1, and it is generated by the element sigma n. Then the image, so the boundaries of the elements of Sn is going to be equal to 0. Okay, so everything is going to 0, everything is going to 0. So in other words, the cycles are just S and X, so everything is going to 0, so this is equal to this. So let's calculate the boundary. Okay, so if n is odd, what about Sn plus 1? Okay, so it should be Sn plus n plus 1. So if n is odd, then n plus 1 will be even. Okay, so now I want to calculate the elements of Sn of x, which are images of elements of Sn plus 1x. Okay, so what are the images? We know that when n is even, then every element, so the generator of Sn plus 1x, which is basically equal to sigma n plus 1x, so sigma n plus 1 will go to the generator of Snx. So in other words, we can say that the boundary is equal to Snx, okay, because Snx is generated by one element sigma n, and sigma n is image of sigma n plus 1, because n plus 1 is even, and in the case of even we have the image is equal to this. So that's why we can say that the boundary is also Sn of x, and in this case we have 0. Okay, now there is one thing left. When I assume that n is even, then I assume that n is not equal to 0. Okay, so let's discuss the case when n is 0. So let's discuss what will happen when n is equal to 0. So when n is equal to 0, then what is the kernel? So of course the kernel of this is, okay, so the kernel of partial 0, so z0 of x is equal to s0x, because everything is going to 0. So what are the boundaries? So partial 1, so basically when n is odd. So when n is odd, then we have seen that when n is odd, then everything, so the boundary of s1 of x, so everything from s1 of x is going to 0. Okay, so let's see if it is true. So we have already calculated Sn, and we calculated the boundaries, and we have shown that when n is odd, then everything is going to 0, and in this case this is 1 is odd, so that's why everything is going to 0. So in other words, the elements of s0 of x such that which are images of elements of s1 of x is only 0. Okay, so b naught of x is equal to 0. Okay, so that's why we can say that if b naught of x is 0, so we can say that h naught of x is equal to z, which is the rank of s naught of x, quotient with this 0 group, and so this is isomorphic to z. Okay, so we have proved these three cases when n is even, and of course in this case we assumed that n is not equal to 0. Okay, so n is even, then we have 0, n is odd, then we have 0, and in case when n is 0, then it is isomorphic to z. So that's what we wanted to prove, and that's what is exactly what is dimension axiom. Okay, so we have proved the dimension axiom for the singular homology. In other words, in the axiomatic definition of the homology, a singular homology satisfies this axiom number 7. Okay, so now we have a little definition of acyclic space. So a space X is acyclic if all the homology groups whenever n is greater than or equal to 1 are 0. So we can say that every one point space is acyclic. Okay, so our next aim is to understand the effect of homology groups of x and y if there is a continuous map from x to y. Okay, so let's see what happens. So we have a topological space X, and let's say we have a topological space Y, and when we are calculating the homology, we have to calculate Snx, Sn minus 1x up to so on, and we have the boundary maps. Okay, so Sn plus 1 up to so on. So we want to calculate these groups, and we want to calculate these maps as well. So what are the elements of Sn of x? So these are the singular n simplices. So in other words, we have to calculate the images of standard n simplices to the topological space. Okay, and we are basically collecting all of these, and we are generating a free abelian group from these, which is called Sn of x. Okay, now if I have a continuous function from x to y, which is f, and this sigma n is also continuous, so this composition, so we know that the composition of continuous functions is a continuous function. So I can take a function sigma composition f, which will start from the standard n simplex, because the domain of this sigma n is standard n simplex. First we will go to x, okay, and then from x we will get some image, okay, so some image of this standard n simplex inside x, and then when we apply f on these points, then I will get points of y. Okay, so it will go from standard n simplex to y. Okay, so we have a continuous function which is f composition sigma n from standard n simplex to y, which is by definition a singular n simplex inside y. So given a singular n simplex inside x, I can calculate a singular n simplex inside y. Okay, so that's an important observation. So let's go further. Now I can extend this composition by linearity. So in other words, what I'm saying that I can calculate, so far what we have done is, given any singular n simplex inside x, I can calculate a singular n simplex in y. So give me a singular n simplex in S and x, I will give you a singular n simplex inside S and y. But the elements of S and of x are basically, it's a free Abelian group generated by the singular n simplices. Okay, so the elements of S and x will be of the form a1 sigma 1 plus a2 sigma 2 plus an sigma n. Okay, so and then there are some conditions as well. So this is a particular element, but so far I just know how to calculate or how to take this sigma 1, which is a singular n simplex on x, and take composition with f to make it into a singular n simplex inside y. But I don't know how to calculate the image of this whole element, which is the integer combination of these singular n simplices. So here's how we do it. So we extend this by linearity. So extend by linearity means if I have a general element of Sn of x, I assume that this f lower hash, which is equal to f composition sigma. So whenever I want to calculate the image of a singular n simplex inside x under this f hash, then I just take composition. So f hash is linear, so in other words, I can take out these integers and apply this f hash on sigma 1. Now I know how to calculate this, because this is just equal to f composition sigma 1, this is just equal to f composition sigma 2, up to so on, and this is just equal to f composition sigma n. Okay, so notice that this f hash depends on n, but for simplicity we choose not to write the subscript with f hash. So just like sometimes we ignore the subscript n for the boundary maps partial. So what we have done so far, so we realize that every singular n simplex inside x can be realized as a, or can be taken to a singular n simplex on y if we have a continuous function from x to y, and then we have a homomorphism from Sn x to Sn y. So let's explore further what will happen if there is a continuous function from a topological space x to y. So we have already discovered that if there is a continuous function, then I have a homomorphism from Sn x to Sn y, and of course I can do it for each and every n. So I have a homomorphism from Sn minus 1x to Sn minus 1y as well. Okay, now I want to show that it is a commutative diagram. Okay, so I can calculate the boundaries of this. So I have a one chain complex. Okay, so Sn plus 1 of x up to so on, and then I have another chain complex corresponding to y, and now I want to show that each and every part is commutative of this diagram. Okay, so let's see how to show that. It is sufficient to prove the result for one element sigma belongs to Sn x. Okay, and then of course by linearity it will be enough that it holds for each and every element of Sn x. So but let's see how to show this result for this sigma belongs to Sn x. So when I calculate the boundary of this, then this is equal to minus 1 raised to power I, and I is equal to 0 to n, because this is a singular n simplex, and this sigma restricted to v0, v1 up to so on vi up to so on vn. So that's how we calculate the boundary of this singular n simplex. Now I want to calculate the image of f hash of this element. So let's see how to calculate this thing. So f hash applied on this thing. Okay, so this is equal to f hash applied I is equal to 0 to n minus 1 raised to power I sigma restricted to v0, v1, vi hash vn. Okay, now f hash is linear. We defined it to be a linear because we defined that we defined it using the extension by linearity. Okay, so let's go back and see. So this f hash, so we defined it to be a linear. Okay, so the constants will be taken out and it will be applied only on the elements on the generator. So I can write it down as using the linearity. So minus 1 raised to power I, so which are just the constants, so I can write them outside and then apply this f. Okay, so let's go back and see. So apply this f hash on the sigma restricted to v0, delete this vi up to so on vn. Okay, now how did we define this f hash when applied on a singular n simplex? So of course we know that this is equal to f composition sigma. So basically this expression becomes minus 1 raised to power I f composition sigma. Okay, so f composition is sigma, and this sigma is restricted to this thing, so we can say that f composition sigma restricted to v0, v1 up to vi hat vn. So that's what we have when we apply this boundary map first and then apply the f hash. Now let's see what will happen if we follow the other route. So we have an element is sigma over here, so let's apply f hash on this. So when we apply f hash on this, then basically this is just equal to f composition sigma, and then I want to calculate the boundary of this. So if we want to calculate the boundary of f composition sigma, so I can just write it down as f sigma. So this is equal to minus 1 raised to power I is equal to 0 to n, and f sigma restricted to v0, v1 up to delete this vi up to so on vn. Okay, so I can write it down as I is equal to 0 to n minus 1 raised to power I, and I can write it down as f and sigma restricted to v0, delete this vi, and thus vn. Okay, so why is this the case? Because this is just a composition. So if I have a function f from this space to this space, okay, so this is sigma from this space to this space, and then I have a function f from this space to this space. So if I have f composition sigma, and if I restrict the domain of this, which means I'm restricting the domain of the composition, which means I'm restricting this part. So this is the domain of the composition. Then this is the same as restricting the domain of sigma. Okay, so either I can say that I'm restricting the domain of the composition, or I can say that I'm restricting the domain of sigma to v0 up to vi deleted and vn, or I can just say that I'm restricting the domain of f sigma. So it is the same thing, and you can easily see that this is equal to this expression, okay, so which we calculated by following the other route, okay, so which is equal to, first apply the boundary on this sigma and then apply the f hash. So these two expressions are equal, so that's why we can say that this diagram is commutative. Okay, so let's proceed further with our goal of finding the relation between the homology if there is a continuous map between the two topological spaces. Okay, so this is a consequence of our previous result. So let's see how to prove this thing. So far we have proved that if there is a continuous function from x to y, then we have the following commutative diagram. So this is the boundary, so this is f hash, this is s and y, and this goes to Sn minus 1 y up to so on. So this is f hash and this is the boundary. Okay, now you can see that first we have to prove this thing. Okay, so in other words, we have to show that if I have a Zn of x contained in Sn x, and this is the set of elements of Sn x such that the image under this partial n is 0 in Sn minus 1 of x, then if I apply this f hash on this thing, so this f hash of Zn x on the, so when I apply this f hash on the cycles of Sn x, then this is also contained in the cycles of Zn y. Okay, so which is contained in here. So that's why I want to show that this is contained in this thing. Okay, so starting from a point, so let's say sigma belong to Sn x such that boundary of sigma is 0. Okay, so let's follow two routes and let's try to see that why this result is true. So we have two routes from sigma to approach this Sn minus 1 y. So if I follow the first route, which means if I first apply the boundary and then calculate this f hash, then this must be equal to 0, because this is a homomorphism, and this homomorphism must take the 0 of Sn minus 1 x to Sn minus 1 y. Okay, so we have proved this. So using the commutativity, this must be equal to applying f hash on sigma first and then calculating the boundary of this thing. Okay, now f hash sigma is an element of Sn y. Okay, and when we apply the boundary, the answer is 0 due to the commutativity. So this implies that f hash sigma is equal to, so sorry, it belongs to Zn y. So that's what we have proved. If I have any element, okay, so normally we use this sigma to represent a singular n simplex, but in this case this sigma is any element of Sn x. So if I have any element such that the boundary is 0, then the image under this f hash of this sigma is basically 0. So the boundary of this f hash sigma is 0. In other words, f hash sigma belongs to Zn y. Okay, so we have proved this result. Now in order to show this result, we will use the same strategy, but we need another element of this chain complex, which is Sn plus 1. So this is Sn plus 1 of x, and over here I need another element, so Sn plus 1 of y, and these are the boundary maps, and this is f hash, and this diagram is commutative. Now let's see how to show this result. So let alpha belongs to Bnx. So alpha is a boundary, so which is contained in Sn x. So what does this imply? So this implies that there exists, let's say, let's call it gamma belongs to Sn plus 1 of x, such that when I take the boundary partial n plus 1 of gamma, then this is equal to alpha. Okay, so there exists a gamma over here, and we have alpha over here, which belongs to the boundary. Okay, so if I follow this route, then what will I get? And if I follow this route, then what will I get? Let's see what will happen. So if I follow this route, so instead of following this route, so let's follow this route. So when I apply f hash on this thing first, then f hash of gamma is an element of Sn plus 1 y. Okay, now when I apply partial n plus 1 on this thing, then it says that, okay, so this element which is first applying f hash and then applying partial n plus 1, so this belongs to the boundary. Okay, so the boundary Bn of y. So why this is true? Because this is image. Okay, so this element, which is an element, of course, Sn of y, is image of an element f hash of sigma of Sn plus 1. So it has an element f hash of sigma. Okay, and when we take the boundary, then of course this element must belong to B and y. Okay, so that's first observation. But then according to the commutativity of the diagram, so this thing is equal to first taking the boundary. Okay, so f n plus 1 of gamma, and then basically calculating the image under f hash. Okay, so f hash. So this is an element of, so this is an element of B n x, and when we when I apply f hash on this, then I have seen that this is an element of Bn of y. So if you take an element of Bn of x and apply f hash on this, then this belongs to Bn y. So give me any element of Bn x, so the boundary is in x, n boundaries in x, then the image under f hash will give me n boundary in y. So this implies that f hash of Bnx is contained in Bny. Okay, so that's one step further in exploring the relation between the homology, given that there is a continuous map between two topological spaces. So let's explore further, and we know some recalls from the category theory. So what is a category? It has objects, it has morphisms, and there is a composition map satisfying certain properties. And what is a functor? So because a category has elements and morphisms and composition rule, so that's why it should respect all of these things. So for objects I should get images of objects, for morphisms I should get images of morphisms, and it should also respect the associative property, and the image of identity should be identity. Okay, so that is what is a functor. Now we have the following main result. So if we have category of topological spaces, then there is a functor from the category of topological spaces to the category of abelian group. Okay, so give me any topological space, I will give you the image of this topological space to be this functor, and this is true for each and every n. Okay, so we will do the proof for fixed n, and of course you can take this n to be any integer greater than or equal to 0. So n is fixed in these calculations, and we can take this n to be any integer greater than or equal to 0. So give me a topological space, I'll give you an abelian group Hn of x, so the nth homology group. And if there is a continuous map between two topological space, then it will give me a map. Okay, so we shall see that it will give me a map from nth homology group to the nth homology group of y. So we have this map as well. Okay, so we have images of elements or objects, and we have images of morphisms as well. So let's go further and try to prove this theorem. So we have already associated topological spaces with abelian groups. So what is that association? Calculating the homology. Okay, so this n is fixed, so basically we are saying that for fixed n we can calculate the nth homology. So we already have images of objects of the category of topological spaces. If I have a continuous function from x to y, then its image under Hn is defined like this. And how we define this image? So basically what is Hnx? So this homology group is defined as cycles quotient the boundaries. Okay, and similarly of course we can define, so we have Hnx is equal to Znx, so cycles quotient the boundaries, and this map goes to Zny quotient with the n boundaries of y. Okay, so which is basically Hn of y. So now how we define the image? So of course the elements of this Hnx are basically the classes. Okay, so what are the classes? So if I have any element, so class of z, so basically this is equal to z plus b and x. Okay, and when I take the image of h and f, which is basically given any continuous function from x to y, then I have this function from h and x to h and y. So how we define this? So when applied on this class, this will give me f of z and this thing. Okay, so it should be basically f hash z. Okay, so f hash z, so and this thing. So what is z? So basically z is an element of, okay, so z is an element of Sn of x, and when I calculate f hash of z, then basically it is any element of Sn of y. So we have already seen this thing. Okay, so this is basically an element of Sn of y, and I'm taking this class. Okay, so I'm taking this element which is basically a class in h and y. Okay, so what is that class? So the class of f hash z. Okay, so let's see how this map is well defined. So we have already seen that if I have, so let's use another color. So if I have an element of z and x, then it will take elements to z and y. Okay, so basically I'm talking about the map f hash. So f hash takes elements of z and x to elements of z and y, and we have already seen that it takes elements of b and x to the elements of b and y. Okay, so they are contained in this thing. Okay, so of course the only problem could be here is that if I have two different elements of the class. Okay, so if I have an element z and another element z plus let's call it z prime of basically the class. Okay, so this z prime belongs to b and x. Okay, so z prime belongs to b and x, such that the class of this is equal to the class of z. Okay, so I have basically z plus b and x, so I can take an element of b and x and add it into z, and it will be the same class. Okay, because the one class of z is basically z plus b and x. Okay, so if this happens, then I should get the same image for both of these representatives of the same class. So let's calculate what will happen with this element. So if I calculate f of z plus z prime and plus b and y. Okay, so this is equal to f hash of z plus f hash of z prime plus b and y. Now due to the fact that when I apply f hash on the elements of b and of x, I get the elements of b and of y. So basically this is an element of b and of y. So of course f hash z and f hash of z plus z prime, they represent the same class because this is an element of b and y, so I can just write it down as f hash of z plus b and y. So basically this is equal to, so this implies that this h and f is well defined. So so far we have images of objects of the category of topological space, we have images of the morphism of the category of topological spaces. So let's go further and try to prove other conditions to show that this Hn is in fact a functor. So now we need to show that this is a homomorphism, so I am leaving this as an exercise for you, and we also need to show that it satisfies this condition, and also need to show that it satisfies this condition, and all of these conditions are very trivial to show, and that's why I am leaving this as an exercise for you. Okay, so also this Hn, if I have a function from x to y, and this Hnf is a functor. Okay, so the image of this morphism is basically direction preserving, so that's why I can say that if it is direction preserving, then this is basically a covariant functor. So let's recall another definition that we are going to need further. So an equivalence in a category is a morphism f from a to b for which there exists a morphism g from b to a such that their composition, so both of their compositions are identity. Okay, so for example, if we have a category of topological spaces, then if I have a continuous function from x to y and a continuous function from y to x such that their compositions are identity, then we can say that it is basically an equivalence in the category of topological spaces. And also, if A and C are categories and we have a functor of either variance, contravariant or covariant functor, then f is equivalence in A implies that Tf is an equivalence in C. So in other words, if now we have a functor Hn, okay, so from the category of topological spaces to the category of abelian groups, so if I have an equivalence in this category, then the image under this Hn will be a category in this category of abelian groups. Okay, so if x and y are homeomorphic, so homeomorphic means if two spaces are homeomorphic, if there exists a continuous function and the inverse of this function is also continuous. So f inverse y to x is also continuous, and of course if f and f inverse are inverses of each other, then these are identity maps. So this is identity, and f inverse composition f is also identity. So this is just a consequence of the fact that x and y are homeomorphic. So homeomorphic means topologically they are the same objects. Okay, so if they are topologically, if they are the same objects, then this theorem implies that if we have a functor from one category to another category, then equivalence in A implies the equivalence in C. So this theorem says that if we have two spaces which are equivalent in top, now we have an equivalence. Now if we have an equivalence f from x to y in the category of topological space, then h and f is going to be an equivalence of h and x and h and y. So what does equivalence means? So it means that there is a function from h and x to h and y which is a homomorphism, and there is another function g from hn of x to hn of y which is a homomorphism, and the composition of these two functions is identity. Okay, so hn and hnf composition g is identity, and the composition of g which h and f is also identity. So that's what it means by this theorem, that if we have a functor from category A to category C, then if f is equivalence in A, then this implies TF is an equivalence in C. So f is equivalence in the category of topological space, then H and F is equivalence in the category of these abelian groups. So these conditions imply that Hn of X is isomorphic to Hn Y. Okay, because we have homomorphism, we have inverse of the homomorphism, and their composition is identity. Okay, so not inverse, because this G may not be inverse function. So we have a morphism, and we have a morphism from Hny to Hnx, and their composition is identity. So that's why this is an isomorphism of the groups. Okay, so thus the group Hnx is a topological invariant. Okay, so if two spaces are topologically same, which means that if they are homeomorphic, then their homology groups are isomorphic. This is very important observation, and we also know that the rank of these homology groups is called Betti number. So in other words, we can say that Betti number is a topological invariant. Now we have a warning. So the converse of above is not true. So there exist non-homeomorphic spaces with same homology group. So the converse of this does not hold. Okay, so let's come to our next section of today's lecture, path connectedness and homology. So we know that a space is path connected if there is a path between any 2 points. So what is a path? A path is basically a continuous function from 0, 1 to that topological space. So since it is continuous, so it will start from one point, which is f of 0, and it will continuously go to the other point without any break to the point f of 1. So if we can find path between any 2 points, then this is a basically path connected space. So for example, in this case, this is a path connected space because I can find paths between any 2 points. Okay, but if we remove this bridge, then this is basically not path connected space. So for example, I can't find the path from this point to this point. Okay, so that's what it means by a path connected space. Now if we have path connected components, okay, so what is a path connected component? So it's the maximal path connected part of the topological space X. So in other words, in this case we have two path connected components. Okay, so I'm using the word maximal. So in other words, you can't say that, okay, let's take a subset of this, and this is path connected component of X, because this is contained in some bigger path connected subset of X. Okay, so this shaded portion is not path connected component because this is not maximal. Okay, so if we have path connected path components of X, then for every X we have this result. Okay, so as you remember that we have already proved this result for simplicial homology as well. Okay, and the proof of this is very simple in this case. So what we are trying to prove, that if we have a space which has components, let's say x1, x2, x3, x4 up to so on, and this is the topological space X with many components, then we want to show that the homology group can be written as this sum. Okay, so the first observation is if we have a continuous function, okay, so a continuous image, so this is the general result for topological space. So if f is continuous, okay, so continuous image of a connected set is connected. So that's first and very important observation. Now if we consider these sigmas, which are basically continuous function from the simplicial and complex to the topological space X, now these standard and simplices are basically connected spaces. Okay, so and these are continuous functions, so that's why this sigma of delta n must be contained in x lambda, where x lambda is path connected component. So this is path connected component of x, because the image of delta n under this sigma must be contained in some path connected component, because the image of this is connected. Okay, so that's why it is true. Now let's go on and see that how to prove this result. So I can write down, I can take any element, let's take it gamma from Snx, and I can write down this gamma as gamma 1 plus gamma 2 plus gamma 3 up to gamma, let's say n, where gamma 1 belongs to Sn of x1, gamma 2 belongs to Sn of x2, up to so on, and this gamma n belongs to Sn of xn. So where x1, x2, x3 up to so on, xn are path connected components, so these are elements of this set, are path connected components. Okay, so every element of this free abelian group can be written in this form, where each and every gamma belongs to this free abelian group generated by all singular simplices inside x1. Okay, because it cannot happen that the image of this sigma belongs to two different sets. Okay, so this is not true, because it is a connected space, so the continuous image of a connected space must be contained in one of the connected components. Okay, so we can write down a gamma like this, and now given any gamma belongs to Snx, we can write it down as gamma is equal to gamma 1 plus gamma 2 up to so on plus gamma n, and if I calculate the boundary of this gamma, then this is of course equal to boundary of gamma 1 plus boundary of gamma 2 plus boundary of gamma 3 up to so on plus boundary of gamma n. Okay, so this n and m should be different, so let's call it m. Okay, so this is equal to 0 if and only if partial n gamma 1 up to so on, so all of them are also 0. Okay, so this implies that gamma belongs to Zn of x if and only if these gamma, these partial n gamma i's belongs to Sn of xi. Okay, so that's our first observation. Also we can prove that the same kind of result holds for the boundaries. Okay, so I can write down, so if gamma belongs to the boundary of Snx, okay, so contained in Snx, then this gamma can be written as a sum of elements which are boundaries inside n. So basically I can write down gamma. Okay, so if this belongs to the boundary, then once again okay, let's call it beta. Okay, because otherwise it will create confusion. So this beta is equal to beta 1 up to so on plus beta let's call it k. Okay, so such that beta I belongs to the boundary of xi, where once again these xi's are the connected components of x. Okay, so using all of this observation, we can define an isomorphism from h and x to the summation h and x lambda. Okay, so how to define this isomorphism? So consider the image of the elements of this. So these classes, so z let's call it lambda, so and this is equal to the class of z1 plus z2 up to z lambda. Okay, so I'm leaving this as an exercise to fill in the details, okay, for example this, and to show that this is an isomorphism. Okay, So that's the end of our proof. So in general, the homology groups are not easy to calculate even for path connected spaces, but we can calculate H naught X using the following discussion. Okay, if X is non-empty path connected space, then homology group, the zeroth homology group, is isomorphic to Z. Okay, so what are the generators? So take any point of the space and that will be the generator of this homology group. If I have a space, then the group H naught X is a free abelian of rank is equal to cardinality, where is basically is the family of path connected spaces. So in other words, what I'm saying is, if let's say we have 3 path connected components, so this is our space. Okay, so let's say this is the space X and these are the path connected components, then H naught of X will be isomorphic to Z plus Z plus Z. Okay, similarly, if it has 100 path connected components, then the rank of this will be 100. If I have X and Y, which are path connected spaces, and if I have a continuous function from X to Y, then F low star from H naught X to H naught Y takes a generator of H naught X to generator of H naught Y. So let's recall some things from lecture number 5. If we have a space, then we can define this pi naught X to be the set of path components of X, and if we have a continuous function from X to Y, then we can define this thing which will take the path connected components or the path components of X to path components of Y, and this pi naught is basically a functor which will take a topological space and it will give me a set, and that set contains the path components of the topological space X. So basically you can see that there is a similarity between H naught and pi naught. So let's see what's the relationship between them. Okay, so the group H naught carries the same information and builds a free abelian group from it. So basically you can say that the information that pi naught and H naught carries is the same information, but H naught X is always a free abelian group. So same information, but H naught X is a free abelian group. So of course, as a simple exercise, we can calculate the homology H naught of S naught. So what is S naught? It is just 2 points. Okay, so let's call it -1 and +1, and it is a topological space with the 2 path components. So by using the above result, we can say that this is isomorphic to Z plus Z. Okay, so this is the zeroth homology of S naught. So next time we will try to see that the singular homology satisfy the homotopy axiom as well, and we will try to calculate singular homology as a consequence of these results. So this is the end of the lecture. Thank you very much, and Allah Hafiz.